The last chapter we're going to look into in the book is the chapter on network security. Now, security covers a very wide range. You use it all the time. Passwords for security. You have a chip in your credit card or your debit card. For example, when I access PC Network from my home, I have to log in with my password, and then, not all the time, but sometime, I get an automatic call to my cell phone, and I have to hit the pound sign to complete my login. This is an example of using something you know and something you have. That's the way they describe it. Now, we're probably not too far off from when we're going to be using iScans and thumbprints as our passwords. I suspect that's coming. The next question after access and availability is authentication. Is the sender who they claim to be? Not a few years back, I got a message from a professor in accountancy who I knew well, and I was a little worried, so I sent her a question and said, "Did you send me a message?" And she said, "No." Somebody had pretended to be her to send me the message. I got one of these recently from a friend I have, a colleague at Holy Cross University. And the message told me to buy several gift cards from Amazon and send them to an address, and I had to do it that day. Well, I started smelling something funny. I noticed that my colleague wasn't using the college email he had, so I did nothing. And then I did something, but I caught on fast enough not to actually buy the gift cards. And then I sent an email to my colleague, and he said, "No, I didn't do anything." So I could have run out a lot of money in that one. Of course, my problems are minor. If you're sending a request to your broker to buy 1 million shares or to sell 1 million shares of a particular stock, and the next day the stock shoots up, well, let's see, you might deny that you sent that message, and then there's a big lawsuit. Now, the other thing that many people, I think many people think of this as the security problem: confidentiality. We don't want somebody reading our email. We especially don't want somebody getting our passwords for things like our ATM or our credit cards. So that's a very big thing. That's where cryptography comes in. Then there's message integrity. Now, this is sort of related to the authentication. It says, is the message we got the one that was sent? Can we determine if somebody made a slight change in it? It may have come from the right person, but along the way it was hijacked, and somebody put a little change into it. That's a hard one. Now, I talk about cryptography. This is a very fascinating topic. It's been around for a long, long time. Some of you probably know that we can trace codes back to at least the time of Julius Caesar. And we still talk about Caesar codes. But I'm going to go not that far back. And there's a funny thing in many parts of publications of many parts of computer science. Every time you read something on a particular item, you get the same examples, or the same people are talked about, or the same cases are studied. In cryptography, we are always worried about Alice and Bob communicating to one another. And there's always an intruder, and what better name for an intruder than Trudy? And you'll see this over and over again when you read any kind of article on cryptography. I wouldn't call it a joke, a standard joke. I just say it's just there. Now, we want to send a message. We call that message the plaintext. What we're going to do is do something to that message to turn it into the ciphertext. Well, how secure do we want the message to be? The best method we could have is the cipher-only attack. In other words, all you have is the ciphertext. You don't know what I put into there, what my plaintext was. You have to really work hard. But languages have patterns. There are certain words that appear regularly. There are many letters that are more often than other letters. We know how sentences are put together. Those are the methods that people can use in cipher-only attacks. Now, one step higher than that is that you somehow know what was sent. This may be that you have, you know what kinds of messages are sent. There's a story that in World War II, the British code-breaking group at Bletchley Park, England, where Alan Turing was, got the idea that the German submarines were sending the weather reports back to Germany. And that gave them something that they could try look at and compare to the ciphertext and see if they could see a pattern. Now, the most difficult one to prevent is the chosen plaintext attack. In this case, the attacker can not only read encoded messages, they can encode messages themselves. Now, that seems like there'd be no reason for this, but it's the way that the public key cryptography, which is the base that protects most of what we do, works. I'll talk in a while about the RSA, Public Cryptography Code. Now, what kinds of things have been happening? In 1993, the National Institute of Standards and Technology, NIST, endorsed a code called Data Encryption Standard. It used a 56-bit key, and it did 16 rounds of applying these things. Between the rounds, it would rearrange the bits. It did all kinds of things. And it was hoping that that would keep the code unbreakable. Now, unfortunately, in 2002, using brute force, 56-bit key encrypted phrase was decrypted. You can see it in this particular article. I warn you, it took a lot of work. In fact, they did it as a distributed algorithm with a lot of small computers like the ones we're working on right now, the PCs, working together to break the code. Well, something had to be done. So in 2001, this got the AES, the Advanced Encryption Standard. Now that might also be called triple DES. What they did was use 3 different DES encryptions, different codes and everything. An attack that would break the oldest standard in 1 second would take 149 trillion years to break AES. That's quite a long time. That comes from this article. Well, one article said it would take 1 billion years to break this code on a 10 petaflop machine. Now, a flop is a floating point operation. And penta is above giga and mega, and it's way up there. I think it's like 10 to the 9th or 10 to the 12th. So it's a very, very fast machine. But now that meant we needed to have keys. And how do we send them to people safely? Do we have to get on an airplane and carry it to them? How do we get the keys out? Well, now comes public key cryptography. 3 researchers, I believe they were at MIT, Rivas, Shamir, and Adelson, developed an algorithm that's been named after them, the RSA, public key cryptography. It wasn't the first one, but it seems to be the one that has taken off, and everybody talks about it. It's also one where the bigger the size of the key is, the better off the algorithm is, the safer it is. This is all based on mathematical concepts. There's a problem called factoring a number. Very simple. I give you a number like 28, and you tell me that 28 is 2 times 2 times 7. Now you just factored that number. And I can test to see if you're correct by multiplying the numbers you give me. And my testing algorithm to do that, my multiplication, it's not a complicated algorithm. It's basically a polynomial based on the size of the things I'm multiplying. So it only grows as a polynomial does. That means the testing algorithm is polynomial. Now, the funny question is, we don't know if there is a polynomial algorithm that can find the factorization. We know if you give it to me, you give me your attempt, I can check it. But how do you get it? This is a very famous problem, sometimes called the golden grail of computer science. It's a problem called the NP equal P problem. What it's saying is that if a problem can be tested in polynomial time, if the answer to a problem can be tested in polynomial time, can it be found in polynomial time? We don't know the answer. Many, many, many problems in the real world are in this category. The traveling salesman problem, for example. The idea of laying out utility lines and what's the best way, cheapest way. These are huge numbers of these have been shown to be NP. And factorization is one of them. Now, if you can solve it, you can get a lot of money. The Clay Foundation up in Boston is willing to pay $1 million to anybody who can do it. They put that out as a challenge for the 21st century. They put out 6 challenges, each worth $1 million. only one has been broken. And the person who broke it decided not to take the money. He's a recluse in St. Petersburg, Russia. So what do RSA algorithms look like? Well, first of all, they've revived an interest in getting primes. You remember a prime number is a number that can only be factored into 1 times itself. There are no other trivial factors. No other factors. Well, we've had them since the time of the Greeks. It's not a new thing. But now we want gigantic ones. We want primes that have 4,000 digits, 5,000 digits. Obviously, I'm not going to do an example that way. But I'm just going to say, to do an RSA algorithm, we pick 2 large primes. We take the 2 primes and we multiply them together, producing the number n. Now, that's not hard. Even if they're 5,000 and 5,000, it's only about 5,000 times 5,000, maybe. It's not above 5,000 cubed, I'm pretty sure. And we compute something called p minus 1 times q minus 1. This is a mathematical item. It's been studied by mathematicians for about 300 years at least. And one of the great mathematicians of all time, Euler, that's a strange name. It's not Euler, it's Euler. He proved that if you give me an E, he can find a D, so that when you multiply the 2 together, you get 1 mod Z, provided Z is in the form a prime minus 1 times a prime minus 1. And that's a mathematical proof. It was done years ago. Now it's very important to the computer science world. It doesn't say how to do it. You might have to do it by brute force, but it can be done. I tell the world N and E. Now you notice that means they don't have Z and they don't have D. If they want to send me a secret message, they take the text T and they raise it to the power E mod N. Now that's not trivial. That's going to take some time. Because remember, we're taking E to the 5,000th power maybe. Or more likely the 5 millionth to the 5 billionth power. So it's a large number. But we can do it. The receiver gets this ciphertext, which remember is T to the E, mod N. He raises it to the D power mod N. Now, text to the E to the D, we multiply exponents in this case. So this is text to the E times D. But E times D equals 1 by the Euler proof. So we get the text. The theory is only we know the D. Everybody knows the E and the N. Well, that's a pretty good idea. There's a small example here. I won't go through it. You can take a look at it. But RSA takes a lot of work. Raising to a large power isn't trivial. So we don't want to do it that often. So what do? We used RSA to create a secret key. And then we use the secret key only once. Before I do that, I want to talk. There's another public key algorithm, the Diffie-Hellman key agreement, which was created in 1976 and was the first successful method. And at this point, people are worried about RSA. It's taking larger and larger and larger primes to make them secure. So there are many mathematicians working on codes based on other items, especially elliptical curves of the form, I think it's y squared equals n times x cubed, or the other way around. But the exponents are the 3 and the 2. There's a whole theory of it, and there's a lot of success. There may even be some that have actually been used at this point. I think there are. Now, as I said, we always talk about Alice and Bob. So how could Alice and Bob create a key that they can use to talk to one another? Well, first of all, Alice and Bob agree on a prime number P and a base G. Maybe they have that, they've exchanged it in something, letters or something. Alice chooses a secret number, A. Now that's sometimes called a nonce, N-O-N-C-E. In fact, in the wire shop, there have been some of the captures that have a nonce in them, if you look. So, she sends Bob G, the base that they have as a secret, to the A power mod P, and the P is a secret. So Bob chooses a secret number B, and he sends Alice G to the B mod P. Now again, he knows G and P. Alice computes G to the B mod P to the A mod P, which is G to the AB mod P. Bob computes the same thing. They now have their number. And Bob and Alice use this number as their key in an algorithm such as AES. I'm not saying it's perfect, but it's better than many ways. And you can see another example I got from the web. Interestingly, P should be around 300 digits, and A and B should be at least 100 digits each. According to one of the sites I mentioned at the top of this, discovering the share secret using GP, G to the A mod P, and G to the B mod P. In other words, even if you know G and P, so I guess they don't have to be secret, they can be public, it would take longer than the lifetime of the universe. This problem is called another mathematical problem called the discrete logarithm problem. What it basically says is, you know the result of G to a power mod P. Now your job is to find out what that power is. And the power is the logarithm of G, a logarithm to the base G of G to the BA. So that's why it's called the logarithm problem. Well, that's what I'll say about that. Authentication has used some interesting concepts. You may have, I hope, heard of a hash function. A hash function takes a number and uses that number and uses some algorithm to compute a new number from it. It's supposed to rely on all the digits in the number you put in. The new number is one use of this, an early use of it is, we don't want to search for items in a huge table. So what we do is we make each item, we hash each item, and the hash tells us where to look. And we have a very large space, a storage space, and we don't fill it up. And there's rules about what happens if two things get to the same number. It's not supposed to happen that often. And you can see things on the web about better hash functions, or even, I think they call them perfect hash functions. Now, as I said, the original use of this was for storage. And I've just made an example there. I think they were used, for example, in the compilers to store the variables. There are a hash function called SHA that produces a 160-bit value. Now there's a new problem. I have to be able to prove that you sent me a message. That's the problem I was talking about above. So how do we do it? Well, what we'll do is one method is Alice sends Bob a message. And then Alice uses a hash function to her, and Bob, known to her and Bob, when she sends the message. Now, Bob, so she hashes the method, and then she uses her private key from an RSA to encrypt her name in the hash message. Supposedly, she's the only one who can do that. Now, Alice also sends a random key for a key cryptography method using Bob's public key. She then uses the random key to send her a message to Bob. Bob gets it, undoes it, and he comes back with her name and the message and all that. And since he's using her public key to decode it, if he gets her name and the message, then the presumption is somebody used her private key. And if someone used her private key, the only one supposed to be able to is her. So the presumption is she sent the message. Now, that's one way. A second way is to pay somebody to take care of it for you. In other words, to use a third party called a certificate authority. That's a trusted entity that basically gives you a way of signing electronic documents so that only you can do it. And the most important part is, if anybody sues you, the certificate authority will defend it and will pay for any problems. There's a site that you can look those up. VeriSign, for example, is one of the groups that does it. This is a little old. I looked at their website earlier tonight, and I think the most expensive one now is around $1,400. GeoSign does it for a lot cheaper. Well, that talks about the authentication ideas. Now let's talk about some of the other things that are used. All of us know about firewalls. There have been times when I've wanted to ram something into a firewall. The idea is that you protect what you have. If something comes in from the internet, the firewall has to look at it. If the firewall isn't satisfied that it's safe, tough. You don't get it. If you want to send something out, it goes through the firewall and then goes out on the internet. So it's a safety measure. It's supposed to be like walling off your whole area to keep people who aren't supposed to get through getting through. They use all kinds of filtering. There's many algorithms. They have to be kept up to date. So that's one thing. Now there's another problem. Did somebody get in and do something? For example, they may be looking at port numbers to see what kinds of things you have available to them. Is there some service they might be able to use? I have a site there for one of the softwares that can do it. That can check for it. There's a case that I heard about many years ago at a talk I went to, where a very determined, some might even say obsessive computer person discovered an intrusion into his network. He discovered it because the billing on his network was off by a couple of cents. And he could not live with the fact it was off by a couple of cents. So he worked and found the intruder. It was a major job, but I'm sure that some of the tools he came up with have been very useful. We have an encrypted password file. If an intruder gets there and can figure out the encryption, then we are in trouble. He can take a password, and he can try it by taking likely passwords, encrypting them, and see if they're in the list. And unfortunately, most of us aren't too keen about making passwords that are crazy, jumbles of symbols. We use things we can remember, and that can make it very easy for people to find things. Some of the kinds of attacks we worry about, the denial of service one is a major one. What this is a hacker will take over a whole flock of computers. He'll get into them. And then he will have each of them send a message to the same site. Well, what that means is the site's going to possibly get overwhelmed, and the site will be out of business. Now, if you are somebody like Amazon, who gets their revenue from the activity on their site, if the site goes down, you're in trouble. There have been talks of companies paying blackmail to some of these denial of service attackers, rather than let it be known that they've had troubles, because it's so important to them to get them back, get their site back. And you can look at some of the ones. Smurf attack is used to generate a fake echo request containing a spoof source IP, which is the target server address. And you can look at that. Distributed denial of service is really the worst part of the DOS. The DOS could be done from one site, but the distributed is the one that is done by compromised PCs. And let's see, in 2001, 359,000 computers were infected with something that was called Code Red in less than 14 hours. It used a known vulnerability in Microsoft. The damages were estimated at $2.8 billion, and that's in 2001. From the 29th to the 28th of each month, it attacked www.whitehouse.gov. A fix for this enabled this attack, of the problem that it was using, was released 16 days before Code Red was deployed. Obviously, it wasn't put in. Now, there are some other kinds of things here. You can look at them. But there's one thing we can't fix: people. If all else fails and you can't find a technical way into what you want, if you have enough money, you might be able to bribe somebody to give you the password that you need to get in. That is one that is very difficult. And some people say everybody has their price. I'm not going to say that because I don't want to be that pessimistic about humans. But unfortunately, that's the one we don't have a technical fix for. There's no way you can prevent somebody from giving somebody else the passwords that they have for their legitimate way in. So that's what I want to say. I think this is going to be the last video that has new material in it. So we have finally reached the end of the string. There may be one more homework, which I will try to put together this weekend. But that will be it. So we're getting very close to the end of it. And I hope that we all make it. Well, we will. We'll manage. So see you later now. Bye.